In 6.5, we're going to look at our fourth kind of factoring. We can sometimes use a type of factoring called difference of squares on our binomials. This has to do with problems we did back in chapter 5 when we were multiplying two binomials that were almost exactly the same. The only difference is one had a plus and one had a minus. So we didn't even need to use all of FOIL. The shortcut was just first and last. So the first times the first in this case would be x squared, and multiplying the last together, positive times negative made a minus 100. So to factor and work backwards, we're trying to think about what times what made that x squared in the first spot. So we know it had to be x times x. And we want to know what times what made that 100 in the last spot. Since we know the numbers had to be identical, they had to be tens. So difference of squares is just describing what's going on here. Difference because we have a subtraction. And squares because what's before and after the minus are perfect squares. So this kind of factoring is very specific. It only works on binomials that have a minus and perfect squares before and after the minus. That means we need to be able to recognize numbers that are perfect squares. So maybe you'd pause for a sec and see how many perfect square numbers you could list out. Like 1 is a perfect square number since it comes from 1 squared. And 4 is a perfect squared number since it comes from 2 squared. 3 squared makes 9. 4 squared makes 16. So we're just thinking about what every number makes when it's squared. And going up as high maybe as 15 squared. 6 squared, 7 squared, 8 squared. Whoops. 9 squared, 10 squared. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. And 15 squared is 225. The more familiar we are with these numbers, the easier this factoring is. On Blackboard and Quizlet, you'll find some games and flashcards to help you practice. When it comes to a variable being a perfect square, the simplest one is just x squared. Turns out that x to the 4th and x to the 6th and x to the 8th are also perfect squares. If you'll notice the pattern there with the 2, 4, 6, and the 8, it really turns out that any even power is a perfect square. It needs to be an even power so that we can split it in half and have identical terms here and here. So any variable to an even number is also a perfect square. Let's try factoring the problems here using difference of squares. First of all, let's make sure it is a difference of squares. I see the minus, and I know x squared and 49 are both perfect squares. So remember, it comes from that FL type of problem. We know there's two sets of parentheses. We know what's in these parentheses needs to match almost exactly, except that one is a plus and one is a minus. So let's think, what should the first terms here be if I get x squared when I multiply them together? Because that's the result of the first and the last. So the way to get x squared is from x times x. And then the last, these two numbers need to multiply together to make 49. And I also know they need to be identical. So 7 times 7. Here's the factors for x squared minus 49. It doesn't matter, by the way, if you put the plus first or the minus first. It would be perfectly fine to write the answer as x minus 7 times x plus 7. Next up, we see we have another subtraction. I know y squares are perfect square, but let's check on 2601. You could try different numbers to see if it works, or you could kind of reverse it by taking the square root of 2601. A lot of times the square root is above your x squared button, so you might need to go second and then x squared, then type in your number to see what you get. Looks like it's 51 square, so we should be able to use our difference of squares here. We'll need y's in the first positions to make the y squared. We know one's a plus and one's a minus. And then the way to get 2601 is multiplying 51 by itself. When you have a higher power like p to the 6th, as long as it's even, you can still use the difference of squares. I also have the minus in the 121, which was on our list there, so it should all be good to go. So that even power, we said we would just split in half. In other words, p cubed times p cubed would make p to the 6th, according to our product rule. We know one's a plus and one's a minus, and 121 is a perfect squared because it's 11 times 11. One more example here together. Let's see. If everything looks correct, we've got the minus, so it is a difference, and all of these numbers and variables are perfect squares. So in the first spot, the 25x squared came from multiplying our first term here by our first term here. To get the 25 part, we'd have to multiply a 5 by a 5. And for the x squared, we need an x times an x. The 196 then is the result of multiplying our last numbers together. So 1 plus and 1 minus. Maybe we need to double check that 196 is a perfect square. Or maybe you recognize it as 14 times 14. So the difference of squares factoring can be very quick and easy once you get the hang of it, especially if you're familiar with those perfect square numbers. On the next page, there's a whole bunch of problems for you to try. Good time to push pause on the video and see what you get. So x squared minus 9 factors to x plus 3 times x minus 3. Or, like we mentioned, it's perfectly fine to have the minus and then the plus. 64y squared minus 225 factors to 8y plus 15, 8y minus 15. Number 3 is a little bit tricky because we're so used to the variable being first. Notice that the b squared is actually after the minus, so the b is going to be in the second positions. And the 100 is before the minus, so the 10s are going to be in the first positions. In other words, we want 10 plus b to be one of our factors, and 10 minus b to be the other. We cannot reverse the a and the b because of that minus. We need to keep the 10s before the plus or minus and the b's after. Number 4, we get 4m squared plus 25 times 4m squared minus 25. For number 5, when we split those 10 c's, we get c to the 5th plus 27 times c to the 5th minus 27. Number 6, you might notice, has a plus instead of a minus. So the r squared and the 49 look okay, but this is not a difference. And you can try any different kinds of factoring that you want, but it turns out when there's a plus, it's not going to factor. In other words, the sum of squares is always prime. So when you notice a plus instead of a minus, once in a while that'll show up. We can't do any factoring. That one is prime. For number 7, we should get n to the 4th plus 6 times n to the 4th minus 6. Number 8's a little bit sneaky with the fraction. Just take the numbers separately. Think about on top of the fraction to make a 1. That would be 1 times 1. And in the bottom or the denominator to make the 4, that would be 2 times 2. So we get a plus 1/2 times a minus 1/2. P to the 4th, we're going to split to p squared times p squared plus 9 for one factor minus 9 for the other factor. 144m squared is all in the first term, so the 12m should be before the plus, and the 13 will be after. And the last one also involves some fractions. So let's see. To make that 100 in the first term, we would have 10 times 10. And then we'll see our plus and our minus. The last term has quite a bit going on. We're going to need something on the top of a fraction to make 25. So that would be 5 squared. And something on the bottom of the fraction to make 196. That would be 14 squared. And then along with those numbers, we also need a c, so that there's a c squared along with that fraction when we multiply it out. There are a couple on this page that actually can be factored more. Once in a while, when you do the difference of squares, the result is still a difference of squares, so it can factor even more. That's happening here in number 4 and number 9. Notice in number 9, the p squared plus 9 is a plus. So that part is a sum of squares. That means it will not factor any further. Let's leave it as is. But the second part has a minus in between a couple more perfect squares. So we can actually continue factoring that factor with the minus in it. And think about what would make the p squared in the beginning, p times p, and what would make that 9 in the end, plus 3 minus 3. Now it looks like we've factored as much as we possibly can. The only square term is a plus, so we know it's finished. And the rest of the terms just have a p, not a p squared anymore, so they're finished as well. Take a second and see if you could do the same thing on number 4. The part with the plus is finished, so let's just bring that down. That factor will be part of our final answer. It's the one with the minus that we can factor a little bit more. 4m squared minus 25 would factor to 2m plus 5 and 2m minus 5.